All right, so we're going to talk about similar figures. What we're going to do in this section, we're going to talk about what does it mean to be similar, and then we're going to talk about how can we use what we've learned about proportions and proportional relationships to help us solve for things between each figures. One of the reasons why we care about similar figures is it allows us to do what's called an indirect measurement, meaning if you know a little bit about one of your figures, you can find out whatever you want about the other figure. For example, if you did not know the length of this, or the length of this, or the length of this. This is used in the real world to find the heights of tall objects, to find the widths of wide, the lengths of long things you couldn't otherwise measure on your own. And it is a valid form of measurement to get at least a very close value for the measurement of something that would be hard to measure on your own. For example, it would be really hard to climb up a very, very tall tree and to get the measurement with a tape measure and get an accurate measurement. But we can use things like the shadows that we'll talk about in a moment. So let's see, when we talk about similar figures, we're essentially talking about figures that have the same exact shape, but they're not the same size. Meaning, think of it this way, one of them will be bigger than the other, so think of it as a blown up version of the other. If you've ever taken a photograph on the computer and you've enlarged it or shrunk it on a photograph, you grab it by the corner and you make it bigger, it's the exact same shape, it's just going to be bigger or smaller. So if, for example, if your photograph is a rectangle, if your photograph looks like this and you enlarge it, it's still going to be a rectangle with the same type of proportional relationship, meaning the aspect ratio of this rectangle will still be the same as this one. And so it's a relationship that does not change. So think of similar figures as one of them is a blown up version of the other. So one of them's got to be smaller, one of them's got to be bigger. So now, this symbol right here, that squiggle means similar. You guys know that the equal sign means equal to, that one's easy. And in class we've even used a squiggly equal sign. We said it's kind of equal to, it means approximately, it means about. It means we're saying about, it's almost equal to. So now when you see the single squiggle is saying, okay, it's not really kind of equal to, it's just kind of like it. Maybe it's similar, it's kind of the same, so it's similar. So that symbol, if you kind of think about the progression of these, is saying it means similar to. And that's the same symbol you use when you get to geometry class. I'm going to go ahead and jump down real fast to one more symbol just so we're on the same page. This symbol right here, it's an equal sign with one squiggle over it. That is an ugly version. Equal sign with a single squiggle over it. That symbol means congruent to. Congruent. That's usually a geometry term. It essentially means equal to. But when we say congruent, we're essentially saying two things are the same. Like this is saying angle A is congruent to angle D. And we'll talk about that in a second. So just know that's just a geometry's way of saying equal to, or they're the same thing, they equal the same thing, they're the same size, the same measure, stuff like that. So that's geometry's way of saying equal to. So now we got those symbols out of the way. Okay, so we know similar figures have the same shape but are different sizes. So here's what you need to know. There are some relationships between these figures. One of those relationships is this. We'll start with the first one. If you look at the first letter of this name, that says triangle ABC. That's a symbol for triangle. This is triangle DEF. A and D, those are the first letters of both of those. The way it's written, so the way it's written matters. Those corners, A and D, they will be equal to each other. And this is what it says, they're congruent to each other. So that means over here, angle A is congruent to angle D. So I'll give them the same marking. Second letter is B and E. So B and E are congruent to each other. So B, I'll give it 2 marks, is equal to E. Those are equal to each other. And then lastly, C and F, they are both the third letters of the names, and they correspond to each other. So C and F are also equal to each other. But if you look, that box, remember, that means 90 degrees. Well, that says 90 degrees. So they're both 90 degrees, and of course they're equal to each other. They're both 90 degrees. So here's what you know. Similar figures, the angles will always be equal. So in similar figures, the angles will always be equal. That's one of the ways to know that they're similar. That's actually an argument you could even make when you're in geometry class and they say, prove this. How do you know? You'll say because the angles will always be equal. So if you have two shapes that all the angles are equal in them, that's a way to know that they are similar shapes. Because think about it, if you took that photograph and you enlarged it, every corner of that photograph was 90 degrees, because let's say it was a rectangle. When you enlarge it to a bigger rectangle, it's still got corners that are still 90 degrees. So that can kind of remind you the angles do not change, but the length of the sides do. So when you enlarge an item, when you enlarge it, all pieces, all linear line lengths, all those will enlarge by the same amount. For example, this one, we stretched out this triangle to get the other triangle. We stretched it out, and so this length of 3 became a length of 6. So you might think, okay, maybe we doubled it, is what it sounds like. So 3 got enlarged to 6, so we doubled it. That same rate of how we increased the bottom side, we also use for all of them. So 4, if we double it, we get 8. And then 5, if we double it, we get 10. So you'll notice they all increase at the same rate, and that's how you know they're similar. And so here there was nothing missing. It was all given to us, but that's what I mean by when I say that the sides have grown at the same rate. You'll notice the symbols, if you name the sides, are right here. Use any 2 of these. So ignore this one. If you just look at these 2, that you can make a proportion out of those. Like let's say you knew this value, you knew this value, you knew this one, but you did not know this one. So that's BC. So that'd be this one right here. If you didn't know this one, and we're ignoring this right one right now, you would have a proportion with one missing value that you would then use the cross product property to solve, just like every single other proportion. Below it though, we just wrote because we know the values of all of them. So that's like saying we could compare these 2 to make a proportion, we can compare these 2 to make a proportion, or these 2. You've got options. So tell yourself, similar figures, all the sides, you can set it up. Now, one thing I want to point out before I'm doing some examples, the things that are on top of each other, so 5 and 10, 4 and 8, 3 and 6, those are corresponding pieces of the 2 shapes. For example, look at 5. 5 is right here. It's the left side of triangle ABC. Okay? Now, look at the left side of the big triangle, ED. That has a length of 10. Because these correspond to each other, they're both in the same position, even if one of these triangles was rotated around, it does not matter. You look at the way they're oriented. This is across from the 90-degree angle, so this one is there. This one's across the 90-degree angle, so they're both in the same relative location. They correspond to each other. Because they correspond to each other, they go over each other. It does not matter if you do little over big or big over little. This never matters with proportions, as long as you do it on both sides. So this can definitely be written like this. And that changes nothing. Okay, so that's similar figures. So if you had an example to where you're missing something about one of the figures, you could solve for it by setting up a proportion. All right, so we'll start with the example here on the right, and then move on to the one on the left. So on the one on the right, we've got 2 figures, and let's say it's given to us that they are similar. We're already given that. We'll talk about how to prove it in a little while. But for now, we're told they're similar. Our job is solve for the missing value. Solve for x. What is the length of that missing side? So what we're going to do is this. We're going to create a proportion. When you do these proportions, you got to remember put corresponding sides over each other. Okay? So when writing proportions, put corresponding sides of each other. In fact, I'll even tell you that. I'll even write that as a note. When writing proportions, put corresponding sides over each other. Corresponding sides over each other. Okay, so what that tells you is this. I always like to start with what I know. We are missing the right side of this one. We know the right side of this one, so that's great. Okay, let's start with what we know. We know the bottom of this one. We know the bottom of this one. These 2 triangles are facing the same direction, so it's easy to tell who corresponds to who. So we'll just call them the bottoms. So we know both of them. So let's start with what we know. You get to choose. Do you want to do little over big or big over little? I'm going to choose little over big. It doesn't matter. This works no matter how you set it up. So that means we've got 4 feet over 12 feet, because those 2 correspond to each other. Now, that right there is half of your proportion. You have a choice whether you want to simplify the 4 feet over 12 feet. You can simplify that to 1 over 3. You're welcome to. It doesn't affect your answer, and it might give you smaller numbers. But just keep things simple so you don't have to worry about also having to simplify at the same time. I'm just going to ignore it. So 4 feet over 12 feet. So we did little over big. So we did, as a reminder, little over big. And so our other side must also be little over big. So we're looking for the right side of this one. We know the right side of this one. They correspond to each other. So these are the 2 values we're going to go in the other half of our proportion. You have to ask yourself which one goes on top. Well, we just said little over big. Well, this 2 feet, that's from the little triangle. So this 2 feet, that's what, excuse me, that's what goes on top. And then we don't know the right side of the big one. So that's our proportion. And just like every single proportion, we're going to use the cross product property. So try this one first on your own. If you think you can take it from here, press pause and see if you can make sure you can solve this one. Make sure you're still not rusty on how to solve proportions. All right, so cross product property, multiply in one direction, 12 times 2. Now I'm not going to quite show as many steps as I usually do. I'm going to just kind of, because I have videos about that, so I'm going to cut out that step where I actually write 12 times 2. Because we know 12 times 2 is 24. So I'm going to go right to 24. Now go in the other direction, x times 4, and we get 4x. Normally I would write 12 times 2 and 4 times x, but I think at this point we've got that step. I've got other videos on how to use the cross product property. Now to solve this equation, we've got to get rid of the coefficient, so we have to divide. So divide both sides by 4. They cancel on that side. And we're left with x equals, let's see, 4 goes into 24, 6 times. So x equals 6. And so that tells us, not only does x equal 6, but the missing length of this side over here is 6. That's the missing length of this side. Now, this one was actually kind of easy. This was one you could have done mentally. I realized that. You say, okay, to get from 4 to 12, I triple it. I multiply by 3. Well, I'll just do that to this one. 2 times 3 or 2 tripled is 6. I know that works with the ones that are easy and simple like this, but don't rely on just being able to do these mentally, because that way may work when they're pretty nice numbers, but it's not going to help you with questions like the example on the left. Those are pretty nice numbers that you can just do in your head and figure it out. Make sure you trust the process of how to set up a proportion. And remember what we said, put the corresponding sides over each other. And you get to choose little over big or big over little. We chose little triangle pieces over big triangle pieces. You should not rely too much on doing 2 over 4 equals x over 12. I would not rely too heavily on that. It might sometimes work, but not always with certain shapes. So be careful and just think about corresponding sides. So let's move on to the other example. If you think you can handle this one, take a moment to press pause and see if you can do this example on your own. And see if you got it. So take a moment to hit pause and try it out. Okay, so now we're going to solve this by first setting up our proportion, and then we're going to use the cross product property to solve it. I did little over big on the last one, so for this one, I'm going to choose to do big over little for this one. So we're going to do big over little. Do it in the other order, just to mix it up and let you know it works no matter which way you do it. So look at what you know first. First thing you might notice is these two shapes are not facing the same direction. They kind of look like boats to me. They kind of look like boats in the water. This boat looks like he's going to the right. This boat looks like he's going to the left. So they're not facing the same direction, but you can still tell which sides correspond to each other. Think of this as the top of the boat or the deck of the boat. So this would be the top of that one. This would be the back of the boat back here. This would be the back of the boat over here. So you can still tell which ones correspond. So use those. Start with what you know. We know the back ends of the boat, or some people might think of it as the height of the boat maybe. So we chose to do big over little this time. So the one from the big one is 4.2. And the back side from the little one is 1.5. So that's how we're going to start our proportion. We're going to do 4.2 millimeters over 1.5 millimeters. Now, on the topic of units of measure, I didn't mean to cut out and not include that. Over here, when we got 6, we were talking feet, so that should be 6 feet over there. Make sure to keep track of your units of measure. They are important because it makes sense. Are we talking feet, inches, pounds, whales, children? What are we counting? Your units of measure is what you're counting. So now our proportion, we did big over little on one side with what we know. It's okay if that was over here. I just like to start with what I know. So now we're looking for the top of this one, but we know the top of this one. Because this is from the bigger boat, it's going to go on top. So 12.6 millimeters. And then the other one's going to be X, since we don't know that one. So now you'll notice in these examples, the units of measure are all the same. So always trying to line up the units of measure isn't going to help you because they're all the same. So think of it as the number from the big shape on the top, number from the little shape on the bottom. So big over little, so the other side must also be big over little. 12.6 came from the big, X came from the little, and that's why it was on the bottom. So take a moment, hit pause, make sure you can solve this proportion on your own. Okay, so we're going to use the cross product property, same as always. So 1.5 times 12.6. So 1.5 times 12.6. And you'll have to bust out your long multiplication with decimals And to be careful to make sure you know what that equals. Then we're going to do 4.2 times x. Well, that one's easy. We know that's just going to be 4.2x. Now, on the left side, I really should have made that blue. 4 points, you know where it came from. So now on the left side, 1.5 times 12.6, you're going to do long. I didn't mean for that decimal to be so high up. You're going to do long multiplication, but you're going to keep track of your decimal. So take a moment to do that. I didn't want to bore you guys with the details of long multiplication. I went ahead and just hit pause and did it for a second. So that's our long multiplication with the decimals. But just remember, the one trick with long multiplication with decimals is once you get your answer, the answer is not 1,890. You got to count decimal places. This one had 1, this one had 1. Add those together, that's a total of 2 decimal places. So your answer must also have 2. So the decimal goes right here. So 18.90 or just 18.9. And so that's what the left side is going to equal, 18.9. Yeah, I don't want to bore you guys with the details doing long multiplication. Practice that if you need it, but for now, just let's focus on the process. So now we have a one-step equation. We have 4.2x equals 18.9. To get rid of all coefficients, you're going to divide. So divide both sides by 4.2. They cancel on the right side, so we're left with just x. Now, so on the left side, we're left with 18.9 divided by 4.2. Give me a second, and I'll do the long division for that. All right, so there's your long division. How to calculate these? Remember what you're dividing by. It's got to be a whole number. So if you have to move that over once on the outside, you must also move it over once on the inside. So that 18.9 became 189. Do your long division, you end up with 4.5. So don't get hung up on the long division. If that's your issue right now, you can practice that. But I want you to focus on what we did. We set up our one-step equation, and then we got x by itself. So we end up with 4.5 being our answer. Now let's answer that in the context of the question. We were solving for, I was calling it the deck of the little boat, and since we got 4.5 and we're measuring everything in millimeters, that means it's 4.5 millimeters is what that tells us. Obviously it's not a very big boat, but I just was calling these boats just to help you explain the shapes. So that was another example of this one. You could not have done this one in your head because those decimals, guys, those aren't things that a lot of us can do quickly in our head. I know that this one was easy over here. I know that you knew 4 times 3 was 12, but over here it was not as obvious how to get from 4.2 to 1.5. So remember we talked about knowing the process that always works so that no matter how hard or easy the question is, you have a tool set that's going to help you get through it. All right, so in these examples, we're given 2 shapes and we're going to set up the proportions and solve them. Now, just like last time, when you write your proportions, remember corresponding sides go over each other. So we're going to do number 4 first. We know the left side of both of them, so those are corresponding sides. You can do big over little, or you can do little over big. It is up to you. So I'm going to call this one big, since I think it's obvious, but just in case. This one's going to be little. All right, so we'll do little over big. We know the left side of both, so that tells us 7 over 21. That's half of our proportion. That is half of the battle. So I'll go ahead and label those with units of measure, centimeters, centimeters. Now, we're looking for the bottom of this one. We know the bottom of this one. So those correspond to each other because you notice it's the widest side, it's the bottom base. So we did little over big, so that 10 goes on top over here since we did little on top. X is from big, goes on the bottom. Now, take a moment, make sure you can solve this on your own. Press pause just to double check to make sure you can do this. So the cross product property tells us 10 times 21, well, that's going to be 210. And then we do 7 times x, which is just 7x. So we're left with 210 equals 7x. Get x by itself, divide both sides by 7. 7 cancels out on the right side. Now 7. Now we know 7 goes into 21 3 times, so add a 0 to it and we got 30. So that means 7 goes into 210 30 times. That's a trick you can use sometimes for calculating some of these. We were talking about centimeters, so 30 centimeters. So the missing length right here is 30 centimeters. That's what that tells us. X equals 30. Now, that one was kind of pretty. You could have done that one in your head. I realized that. So we would have said, okay, 7 times 3 gives us 21. So let's see, 10 times 3, okay, that gives us 30, so the missing side is 30. Some of these you can do mentally, but again, I want to caution you, don't always rely on that because that will not always work as soon as the numbers get ugly. Now, in this example, take a moment to press pause, see if you can do it on your own. So this one may not be decimals, but it may not be obvious. What do you multiply this by to get to that? It might not be obvious, and that's okay. But I want to make sure we have a method that always works. So we did little over big last time. So this time we'll do big over little. We'll do big over little this time. I just bounce back and forth. It really does not matter. Start with what you know. We know the right side of this one. We know the right side of this one. We said big over little, so 18 feet is on top and 12 feet is on bottom. Remember to make sure you hit pause. Please try this on your own. Don't just watch it and treat it like it's a movie. You got to practice. We're looking for the bottom of this one. We know the bottom of this one. This is from the big one, and we said big is on top. So that X is on top. So that means the 14 feet, they correspond to each other, is on bottom. So that's your proportion. For some of us, the hardest thing is going to be how to set up the proportion. We've practiced how to solve them, but how to set it up ourselves, that is sometimes our problem. So if you want to take a moment, press pause, make sure you can solve this one on your own. All right, cross product property. Remember, you don't have to go in this direction first. I just do it out of habit. I think it's because I'm right-handed, but it really doesn't matter. Okay, so let's see, 12 times x, so that's going to give us 12x. Go in the other direction, 14 times 18. Nope, that should be a different color. So 14 times 18, this is going to be a moment for you to use your long multiplication. Okay, so long multiplication, 14 times 18, that's 252. Again, I was trying not to bore you with the details of going through that. If you need a moment to make sure you can get that on your own, take a moment, make sure you can do this. So we got 12x equals 252. Solve that by dividing both sides by 12. Remember, at this point you have a one-step equation, you're just getting x by itself. All right, so let's see. This one you might actually be able to do mentally. Let's imagine instead of 250, that was 240. 240, if that was 240, we know 12 goes into 24 2 times, so that means 12 goes into 240 20 times. So if it goes into 240 20 times, lock that in your mind. If you're not sure, do long division. That means from 240 to 252, well, that's only another 12. So it means one more time. So 20 times plus one more time, that's going to give us a grand total of 21 times. So that means 12 goes into 252 21 times. So let's keep track for our units of measure. And so since we were solving for feet, that's going to tell us 21 feet. That is the length of the missing side, 21 feet. So that was two more examples. This one, there was no decimals involved, but it wasn't super obvious what they multiplied this by to get to this one. Technically, for those of you who really want to try to think about how could you at least put this in perspective mentally, 12 times 1.5 is 18. 14 times 1.5 is 21. Because half of 14 is 7, so 14 times 1.5 is like saying, okay, 14 times 1 is 14, 14 times half is 7, 14 plus 7 is 21. If you don't like doing that mentally, don't sweat it, not a big deal. I was just, for those of you who are trying to get perspective mentally. So these are two more examples. Let's go try two more. All right, so we have a grand total of 2 examples remaining, counting this one. So this will be number 5 is what this one is. So example 5. It says, which triangle is similar to the given triangle XYZ? Now, we said earlier, if they were similar, that they would have a constant ratio. It would all be the same. All the ratios would be the same. So for example, if XYZ were going to be similar to ABC, this would have to be true. We would have to have, here, I'll even color code these. So 30 over 32, because those correspond, that would have to be equal to, I'll put a question mark for now, that would have to be equal to 24 over 26. Now, I just chose to do little over big, but you can do big over little, it does not matter. We're going to check to see, is that true? If that is true, then yes, these are similar to each other. If that is not true, then no, they are not similar to each other. We got fractions, so simplify these fractions. 30 over 32, well, we know 2 goes into both of them, so that turns into 15 over 16. And then we have 24 over 26. Well, 2 goes into both of those, so 12 times and 13 times, so that turns into 12 over 13. Ask yourself, are these equal to each other? These two fractions are clearly not equal to each other, so because they are not equal to each other, that means triangle ABC is not similar to XYZ. So, not similar. Sometimes you'll just have questions that'll say, are they similar, yes or no? Other times you'll have questions where they say, which one is similar? So this first example was comparing XYZ to ABC. So now we're going to compare XYZ to FGH. So I'm going to use the same colors. The left side's in blue on this one, so the left side's in blue on that one. So we'll put 30 over 35. We're going to check to see if that's equal to 24 over 28. Now again, I did little over big. It really does not matter. I'm just doing it out of habit. You could do big over little as long as you're on both sides. So 28. We're going to check to see, are those equal to each other? Now, simplify both of these fractions. 30 and 35, well, 5 goes into both of those. 5 goes into 30, 6 times. 5 goes into 35, 7 times. Over here on the left, 24 and 28. Well, let's see, 4 goes into both of those. 4 goes into 24, 6 times. 4 goes into 28, 7 times. That turns into 6 over 7. Are those equal to each other? Yes, they are. Because of that, yes, similar. So that tells us that triangles XYZ is similar to triangle FGH. Now, very quickly, I'm going to hit pause and I'll just show you for the last one. I've shown you an example where they're not similar, an example where they are similar. So I'm just going to take a moment to show you the last one, but I'm not really going to take the time to explain it. So on the right side, you see that I went ahead and I showed you, in this case, I did big over little. So I did 30 over 10, does it equal 24 over 14? And you notice they do not simplify to the same thing, therefore not similar. So this is the fastest way to check if things are similar, yes or no. You are welcome to use the cross product property to also help you check these. You could have done 35 times 24, and then you could have done 30 times 28 to check, do those equal to each other? And for this one, you would find they do equal to each other. The cross product property would give us a true statement because nothing's unknown, so we wouldn't solve for anything. But because it would give us a true statement, then yes, they are similar. If you did it for this one, 32 times 24, does that equal 30 times 26? You would find out no, they do not equal each other. So you know they're not similar. So remember, similar figures have a constant ratio, a constant proportion. So because this one was not the same, not similar, not the same, not similar, but XYZ and FGH, they were the same. So yes, they are similar. You can use fractions like this, or if they were decimals, you couldn't really use fractions, you could use the cross product property. That would be the method that always works. Okay, so we'll call this example 6. I'm going to slightly modify it. Alright, so in this example, this is showing one of those methods of being able to use indirect measurement to find the heights of objects that would be hard to measure on your own. For example, it would be very hard to climb up a flagpole with a tape measure trying to measure it yourself. It wouldn't be safe either. So this is one of those methods. Now, if you measure the shadows of two objects at the same time of day in the same location, meaning usually next to each other, where the sun's in the same relative location for both of them, you're going to be able to set up a proportion with similar figures to figure out what is the measurement of one of them. For example, you can take a person who you know is 5 feet tall, you can measure that with a tape measure very easily, and measure their shadow. So if their shadow is 3 feet long, that tells you, okay, 5 feet tall, 3 feet long. Now, if you know that, you now can look for something else around you, and you can construct a similar triangle situation. Let's say there was a tall flagpole, and its shadow was 28 feet long. So that at the exact same time of day in the same location on the planet Earth. That one had a shadow of 28 feet long. Well, what you're going to do is this. You're now going to be able to create a similar situation to where you can set up a proportion. So if you haven't already, press pause, make sure you can do this question. So the question says, Tasha wants to find the height of the flagpole at school. One morning she determines the flagpole casts a shadow of, we're going to change that to 28 feet. Cast a shadow of 28 feet. If Tasha's 5 feet tall and casts a shadow of 3 feet, what is the height of the flagpole? Well, like we already said, these are similar triangles. We know the bottom of both of them, so we'll start with that. I'm going to go ahead and do this, solve this one using little over big. It doesn't matter if you do little over big or big over little. Remember that, as long as you're consistent on both sides of your proportion. We know the bottom of this one, we know the bottom of this one. This is the little triangle, this is the big triangle. So that means we're going to have 3 feet over 28 feet. That's half of your proportion right away. What you know, the corresponding sides that you know in both of them, that will always be half of your proportion. So now we're going to solve for the unknown height of the height of the big one. We know the height of the little triangle, and so what we're going to do is we did little over big, so that 5 feet, the height of the little, that goes up top since we said little over big. We don't know the height of the big one, so the height of the little over height of the big, those correspond to each other. We don't know this one, so it's just an x. Just like every other proportion you've ever done, you're going to solve this with the cross product property. 28 times 5, and 3 times x. 3 times x is the easy one. 3 times x is just going to give us 3x. Now, on the left side, 28 times 5, well, let's see. 5 times 20, that's 100. 5 times 8, that's 40. So put that together, you have 140. 140. So 28 times 5 is 140. Now, just like every other one-step equation at this step, you got to get rid of the 3 so you get the variable by itself. So divide by 3. That's the opposite of a coefficient, always. Those cancel. We're left with x equals 140 divided by 3. If you're not sure what that equals, we'll bust out some long division. 3 divided into 140. 3 goes into 1 0 times. 3 goes into 14 4 times. 4 times 3 is 12. Subtract. 14 minus 2 is, 14 minus 12 is 2. Drop the 0, we got a 20. 3 goes into 20. Well, let's see, that's 6 times. 6 times 3 is 18. Subtract, we get a 2. We need more. Put a decimal there, put a 0 after it. The decimal's there, decimal goes there. Drop the 0, we got a 20. 3 goes into 20, 6 times. 6 times 3 is 18. So at this point, you notice we're going to have a repeating situation forever and ever. So that means that 6 repeats. So 46.6 repeating. So that tells us the height of this is 46.6 with the 6 repeating, and we're talking feet. So feet. Now, if the question had said round to the nearest whole number, the 6 tells us to round up. If it had said nearest whole number, it would be 47 feet. That would have been the height of it. If it had just said, maybe write it as a fraction, well, 0.666, when we got a remainder of 2 right here, we would have had a remainder of 2 over 3. So if you wanted to be precise without rounding, you could say 46 2/3 feet. So any of those are acceptable. So this is approximately 47 feet. This is the exact answer, 46 2/3 feet. And this is just a way of using, this method is just using the bar notation for repeating decimals. All right, so long story short, similar figures. One of them is a smaller version than the other, and the corresponding sides, you will always go over each other when you write your proportion. When you write your proportion, corresponding sides go over each other, always. So remember how to write the proportion. That's really the new skill in this section. At this point, you guys know how to solve proportions quite well. So just think about how this one relates. Maybe we were doing scale drawings and scale models. This is very, very similar, and a lot of times they overlap, and the question can be both. It could be a scale drawing or a scale model, or just similar figures. So make sure you practice, and good luck, and remember to study and practice when knowing you're doing